So far we learned what a logarithm is, the fact that it is an inverse of the exponential functions. We also looked at the graph. But now we're going back away from the graph for a bit and going back to the fact that we're thinking of the exponent. Okay, there we go. Lag time is, or something. There we go. So we're going back to the fact that they are inverses of exponentials, and we're going to use that to create a log rule. So the first thing I want you to do is remember, how is it that you deal with this exponent rule? When you have the same base written twice and it's multiplying, what do you do to the exponents? You got it. You add them. Now, very important, very important. There's an operation that is bonding two separate exponentials, and the bond is occurring outside of the exponential. Do you know what operation I'm referring to or where I'm trying to have you look? So two separate exponentials. And they are bonded outside of themselves by what operation? What operation is bonding what I highlighted? You got it. Then I want you to notice that the other bond that is going on is between the actual inputs inside the exponential. And I'm going to highlight that. So m was an input in the exponential b to the x. N was an input in the exponential b to the n. And the other side of this exponent rule is that those insides use what operation? And what, you got it. Addition. And do you see the difference between the inside, an operation occurring inside the exponential versus outside two exponentials bringing them together? Take a good look at that, because understanding that aspect of this rule is going to help you tremendously with understanding the log rule that's coming up. Now, for review, what do inverse functions swap? When you go to find an inverse function, there you go. They swap their x and y variables. So this means that one function's inside swaps with its functions outside. And let me see exactly what I had written down with the classwork. Yep. So to be overly clear, this means that one function's input inside the function swaps with its inverse function's output outside the function. Now, are you ready for your first log rule? Here it is. And I want you to notice here that on the left side, I have two separate logarithms. They are being brought together by addition. It is outside either of the two logarithms, but addition is what's bringing them together. And then when I look at the right side, these parentheses right here are emphasizing that this is inside of the log function. And when they are side by side, we understand that that means a multiplication symbol is between them. So inside the function, multiplication bonds those two inputs. But outside of them as two separate logarithms with each individual input, those two are being brought together by addition. If you see this role reversal swap, it's going to help you tremendously. Unfortunately, what happens is people learn log rules and they learn them more as magic almost, more than anything else. And the more this makes sense to you, the less this is going to seem like a magical step. And the less you're going to accidentally make up a morphed version of this magical step. What I see is a lot of times people will misplace the operations if they don't really understand this log rule. So you need to actually take a good amount of time to focus on this log rule. Look at it next to this rule over here. And I want to emphasize the exponentials are separately brought together by multiplication. That causes their insides to add. With logarithms, when two logarithms are brought together by addition, then their insides are brought together under one logarithm with multiplication. So I want to emphasize some issues with notation because you need to be aware right at the beginning. And I'm going to highlight to show you where I'm looking. When you write a logarithm, you write log base b, and then after that, you go back up to the normal log where that was written line, and you immediately start writing down the input. If you have side-by-side understood multiplication, that's right there as soon as you come up from the subscript, there's an understanding that there is a parentheses around that, and that the order of operation is if you plug numbers into the x and the y, you first do multiplication, and then you take that answer and it goes into the logarithm. Okay, so I'm going to go back over to the blank copy of classwork, and we are going to learn how to expand. Woohoo! Also, I'm going to be, I'm not going to go into the extreme particulars, so things are going to be written down like this, where you don't have to realize why that's important. Just know it needs to be there, but you're not going to let it concern you, basically. So, number one. Expand means you want to, as much as possible, write things as an addition of separate logarithms. You're trying to separate the logarithms. So let me go back over to these rules and make sure to clarify. Expanding happens when you go from this situation to that situation. We're going to gain more log rules as the week progresses. Today, we're focusing on just one log rule and getting used to what expand means. So what you're looking for is any multiplication inside that logarithm, you're going to separate into two separate logarithms. So you look here and you see that that means this is log base 3 of 8 plus log base 3 of x. And I'm going to come back to number 1 and point something out to you when we get through number 2. So that's it for number 1. Then for number 2, instead of 8x, we have 9x. That's the only difference. So we're going to start off the same way of separating this multiplication so that we have log base 3 of 9 plus log base 3 of x. However, with problem 2, you can simplify further. So I want you to look carefully at the difference between 1 and 2. And I'm telling you that 2 can be simplified more where 1 cannot be. Do you see the simplification I'm referring to? And then you know the difference is this 9. That's what's different between 1 and 2. So look at this logarithm, log base 3 of 9. Do you notice anything special about it? You almost have it. You have it, but I think you just thought it wrong. Uh-huh. And if 3 squared is equal to 9, what does that mean the logarithm is equal to? Yep. There you go. So, oh my gosh, I make those mistakes constantly, especially when you've got the number 3 hanging around so much. It's easy to accidentally just keep saying 3. Anyway, so you want to recognize the logarithms that we talked about back in section 3.1. You want to be able to now recognize when they are actually just a nice integer number. And then simplify further. And now that is considered to be expanded and simplified. And just to point out, the directions say simplify your result wherever possible. And I want to also point out that if you look over here in number 1, while 8 is a power of 2, it is not a power of 3. So let me just write this down because the numbers are floating all over the place, and it's really important to keep track of where they are located and what that means. When I look at log base 3 of 8, I can write the 8 as a 2 to the 3rd power. When I look at log base 3 of 9, log base 3 of 9 is log base 3 of 3 squared. So I want you to clearly look at this and realize that these threes are too far apart to do any kind of simplification. These threes are back to back. Because you want to realize that the order of operations is, for number one, this 3 goes into 2 to the power, and then 2 to the power goes in a base 3 logarithm. And if you're just listening to what I'm saying, I'm trying to emphasize the issue of these numbers I'm underlining aren't matching. They're not giving you the side-by-side inverse situation. Whereas here in number 2, 2 goes into 3 to the power of something. 3 to the power of something goes into a log base 3, and those are actually opposite operations. You can look at the expression that I wrote here as a 2 goes into a function, who then goes into its inverse function. They undo each other. And when inverses undo each other, they leave you with what was initially inside, what was nested inside of those two back to back. So I really want to point that out to you. You may want to watch this again later in a couple of days, because it's going to make a lot more sense in a few days when we've played more with these. Okay, number 3. We actually have 4 things multiplying here. So what we will do is we will break it up into a sum of 4 separate logarithms. And now look at who's in front. When you have a number plugged into a logarithm, you need to take a good look at it and see if you can simplify that. And remember, when you're looking at a logarithm where it's just you have a number for a base and you have a number input, that it's actually asking you what is the exponent on this 2 that will give me an answer of 8. What is the exponent that I can put on that 2 to get an answer of 8 from 2 to the power of? So 8 is 2 to the power of what number? And I'm looking in chat. There we go. So because an exponent of 3 on 2 will give me 8, I want to look at logarithms as actual exponents. That is saying the exponent on a base 2 needs to be 3. And from there, the rest of it is just going to stay the way it is. Log base 2 of A plus log base 2 of B, oops, plus log base 2 of C. Okay, now a fourth problem, a little harder. What we're doing with our new log rule isn't the hard part for this one. So with our new log rule, we have 3 things multiplying. That means I'm going to turn this into 3 logarithms that are adding. Now the first logarithm there has a 1/6. And you want to figure out if you can write this in a simpler way. So keep in mind that you can put like a little exponent on there. It's really, that logarithm is the exponent on a 36, where I'm getting out the answer of 6. So what can you do to figure that one out? And I would say that I think the easiest way is to work both sides of this equation. If you're working both sides of the equation, what number is kind of popping up in your head is extremely important. What base number do you need to work with? Good, 6. And this is why you want to be familiar with your perfect square numbers and your perfect cube numbers. So 36 all by itself is 6 squared. And by understanding exponent rules, we know that the 2 will multiply to whatever that exponent is. And then 1/6 is 6 to the power of, what is the exponent on that 6? One-sixth is equal to 6 to the power of, I'm waiting in chat. There we go, -1. So if the bases are the same in an equation, then the exponents are equal. And what does that make this number simplify to? -1/2. And then you just write the rest of it after that. And take a moment to just think about it also and see the correctness of 36 to the -1/2 power. The 1/2 power means square root. The negative with that exponent means flip the fraction. So make sure that you are very clear in 36 to the -1/2 power. Negative means put it in the denominator, but now just change from negative to positive. Then a 1/2 exponent means square root. It's very important that you take the time to let this number sense sink into you. It will allow you to have a much easier time with this chapter if you take the time to let these exponent rules fully embrace you. So that is the end of expanding. And now it's time for condensing. I like condensing more than expanding because you know when you're done that you're done. Condensing is what you're going to do in the opposite direction. So I'm going back over to here. So instead of that direction, we're going the other way. When we're condensing, we're looking for logarithms that are adding together. Whoops, what did that do? Okay. Anyway, so you're looking for logarithms that are adding, and you are going to use the log rule in this direction. You're going to condense two logarithms into one logarithm, but you have to be very clear about the operations. And I want to remind you, you know this exponent rule. This exponent rule, if I'm condensing two exponentials into one exponential, I add the exponents. Logarithms are reversing this process. And remember that logarithms are actually exponents themselves. So you can think of the logarithm as the actual exponent m, and the other logarithm is the actual exponent n. And if they're adding together, then you are able to condense it into a single logarithm where their insides are multiplying. And you almost need to look at this exponent rule. The logarithm is turning this inside out. When you look at this, that has to actually kind of come inside of itself when it looks at its inverse. So it's like if you were to take an inflated ball, cut it open, and then try to turn it inside out, that's a bit of what we're trying to do here. So why does it keep putting me back at the beginning? I don't know. So that's what we need to do when we're condensing. Here we go. You should notice an addition here and an addition here. And if you feel comfortable, you can do this in one step. In one step, you can say all three have base 6 for their logarithm. So I can actually have each of the insides multiplying inside the one logarithm. And then that's condensed. And so I'm starting you off with an easy problem, and then I'm moving to one that's a little bit harder. If you are asked to condense an expression into a single logarithm, that includes a number that is sitting there. But I want you to remember what happened earlier. How did we end up changing a logarithm into a number? And now you're kind of reverse engineering this situation. How do you go from a number to a logarithm that you need? And first of all, you need that logarithm to match the bases that you're working with. So we're going to start there. The base of the logarithms that I'm working with are base 8. I want to write 2 as an answer to a logarithm. So that means I want to look at 2 is equal to a logarithm that is base 8. And I need to figure out what's going in that logarithm to give me an answer of 2. And this is tricky. This one is not easy. Unfortunately, it's not. Let me give you a tip on a way that you can work with this, but you might see a completely different way, and you know what number that is. You have a way that your mind is dealing with it, and your mind knows what that number is. But I'm going to show you a step-by-step process if you don't see it easily. What you want to do is you can write this as, hold on a second. Let me remember where I was going with this. I need to bring my brain back for a moment. Yeah, okay. So what I need to put in here to get a 2 out is 8 squared. Do you see that? And I want to point out that I had mentioned earlier that the order of operations is that this 2 goes into 8 to the power. 8 to the power goes into log base 8, and you have back-to-back inverse operations. And that means that this logarithm is equal to just the 2 that is here. So now you want to write 2 in this way. And you also want to simplify. And by simplify, I mean 8 squared is going to give you 64. And then I'm going to bring the log rule in. I'm adding 3 logarithms together. They are going to condense into a single logarithm that has that same base. And it's going to be 64 times 2t times p. But you are expected to simplify. You're able to multiply the 64 and the 2 together. And it's 128 TP. Oh my goodness, I just realized. Last year at this time when I was going, haha, look, it makes TP, I had no idea how important TP was going to become very, very soon. Oh my gosh, that was so stupid. Quick, everyone, grab all the toilet paper. All that matters is having a clean bottom. Oh dear. Anyway, so there you go. That's simplified. And let's see. Oh, yes. Now, I went over a log rule, just one log rule. And instead of bringing in multiple log rules with you at once, we're going to do a short break from logarithms and talk about a particular graph. And it's not too bad of a graph to look at. So the graph of x cubed is an important graph. As I have figured out how to kind of like piece together things in units, I saw that this was a good place to throw something because you need to focus on one thing at a time with logarithms and then let it go. So we're letting the logarithm go. Shake it out. And now let's go back to some nice fun days where numbers made more sense. What is -3 to the third power? -3 times -3 times -3. What are you guys getting? Good, -27. And then when we pop -2 in there, -2 to the third power is -2 times -2 times -2, and we get negative. You guys have this one. You got it. There we go, -8. -1 cubed, -1. 0 cubed, 0. 1 cubed, 2 cubed, and 3 cubed. So plot the points you are able to plot on the grid. 27 and -27 are off grid, so just plot everybody else. Okay, so we've got 0, 0. We have a 1, 1, and a -1, -1. These 3 points are really, really important points that I want you to be very aware of. Then you have 2 to the third power gives you 8. I'm sorry, I think, yeah, I did say that right. And then -2 to the third power gives you -8. And then what you want to understand about the graph is it actually flattens in the middle. It's actually a bit flat right here in the middle, but it becomes steep pretty quickly. Now you're very familiar with the graph of y equals x squared. I want you to notice that by bumping up x squared to x cubed, when you cube numbers, you're making them even, shall we say, bigger than they were before. So you're kind of making this graph a bit steeper. And then also, when you cube negative numbers, they get to be negative numbers. So instead of getting that symmetry that we had before with a parabola, we have kind of a reverse symmetry situation, where instead of being like both sides doing the same thing, one side turned down, and it's a little steeper. So important features, and I'm going to come over here because I need to make sure that I'm on time with starting your quiz. Did I put more things in there? No, it is just those. Why am I don't know. Okay, there we go. So notice domain and range, all real numbers, negative infinity to positive infinity. And right here at the origin, now this is a graph that is computer generated, so you can see what it definitely does look like. Now, this is called an inflection point. I'm not going to, well, I'll say real quick, the reason it's called an inflection point is because your graph changes from looking like a frown to a smile at that point. You've got a half frown, half smile going on. And right at 0, 0, it actually changes the way that it smiles or frowns. So it's called an inflection point. And know that the slope is actually 0 right there, but only for that moment. So it actually does go flat, but quicker than a moment implies that there's some time involved, but there is no time involved in this moment. It's just right there. It's flat, and then it's going back to growing again. Now, for the rest of your classwork, it's taking that graph and be ready to, in your homework, start with the parent graph that we already drew. And then when you multiply outside the function by 2, you're taking the y coordinates, and the easiest ones to use, this trio. If you multiply all 3 of those y coordinates by 2, y coordinate 0 is still 0, and the plus or minus 1 becomes plus or minus 2. I don't expect you to show the stretch any more than just plotting these 3 points and trying to draw the same graph between those 3 points as you drew here based on these 3 points. And then the next graph has that same multiplication by 2, but now inside with x, we're adding 3. So that means we're going to subtract 3 from the x's. And then outside we have the plus 1, and we are going to add 1 to each of the y values from the previous graph that was the 2x cubed. And so this is all 3 of those points shifting. Do you feel pretty clear? Because I need to open up that quiz. We've got 5 minutes left of class.